Yes, hello. Thank you for the nice introduction and for the organizers to give us this talk about the study, which is about observations of hot exozodiacal dust with the new instrument MATISSE. First of all, because I think not everyone is familiar with hot exozodis, brief introduction. We are in the field of debris, so we have dust located around a main sequence star. The dust is located very close to the star, we think, or it's probably at the sublimation radius, which means that the dust has very high temperatures in the order of 1000 Kelvin or even above. And when you plot the fluxes of these dusty systems in a spectral energy distribution, you will see that the emission peaks in the near infrared and or short mid-infrared wavelength range. In total, this makes it very difficult to observe the hot exozodis, and today there are only 23 systems known with near-infrared excess associated with circumstellar dust. And there are two requirements for successful observations. We need a high angular resolution in the order of 10 milliarcseconds, and the second thing is that we need a high sensitivity between the dust and the stellar emission. This brings us to long baseline interferometry, where we have already, for example, the instrument PIONIER at the VLTI in H-band, but when we want to observe at slightly longer wavelengths, we have now the instrument MATISSE, the mid-infrared spectroscopic experiment, which is operating since April 2019, which observes in LM band and in N band. For the observation of hot exozodis, we have performed an feasibility study before the very first observations with MATISSE, and it came out that it is quite promising that we could observe the hot exozodis with MATISSE. So we wrote a proposal, it got accepted, and we observed Kapatok last summer in 2 nights for 1 hour in low resolution with MATISSE. And we observed in medium configuration of the auxiliary telescopes, which is part of our observation strategy, because there the star is mostly unresolved, while the circumstellar emission is already resolved. The data were reduced and calibrated with the help of the SUV, the VLTI support service of the JMMC. And some words about the N-band fluxes. We expected that the flux is around 1 Jansky, which is an order of magnitude below the sensitivity limit. And that's why we discarded all the N-band data here and focus only on the LM band data. We got then measurements, visibility measurements as a function of baseline. You see here 12 visibility measurements for one special wavelength. And you see a clear difference between, in blue, the bare photosphere of the star and our visibility measurements. And there are two potential explanations for this visibility drop. The first one is there might be a companion, but we couldn't rule it out because the closure phases are very close to 0. That's why we assume circumstellar emission in the field of view. We want to model then the circumstellar emission using a limb darknet photosphere and Gaussian distribution of the circumstellar material in the field of view. This gives us then a function which is shown in the plot in magenta, and we fit our observational data with one parameter only. This is parameter F, which is the dust to star flux ratio. We do this for each single wavelength, and the significance or the criteria for the detection is that we want a flux which is larger than 3 times its error, and this is the case for the wavelength range between 3.37 and 3.85 micrometer. And this is indeed the very first detection of hot exozodi in L-band. We find that the flux ratio is between 5 and 7%, which is quite high compared to the H-band, where we have a flux ratio only of 1 to 2%. And this translates into real dust fluxes between 0.5 and 0.9 Jansky. What we want to do then with our new observations is SED modeling of the system. We consider scattering and thermal emission and took the code debris from Steve. We assume a disk ring with inner radius R and outer radius are only 10% larger, single grain size, and dust masses. This is a very simple model. We want to keep our model as simple as possible because the amount of data is quite low, and the results show, or the best results we got are for amorphous carbon. For other materials, the results are slightly worse, but it's not significant. So we can't really out that silicate is present in our systems. And so what we do is we fit our spectral energy distribution in the right, around 3.5 micrometer. You can see the new observational data. There are also H-band observations in 3 upcoming years. In 2012 and 2014, there was a significant H-band emission, but in 2013 it was insignificant. So it's a problem. So first of all, this is the only system we know with the temporal variability at the moment. And the second thing is this makes it a little bit more complicated to treat the near-infrared variability. And we do this in 4 different approaches. The first one, we consider only the new L-band data, so only the mid-infrared data. This gives us a square map on the left. The dust is very close to the star, only 0.03 astronomical units, but the errors in grain size and also in dust location are very big. When we consider H-band data, when we consider only the H-band data, this is model C, the red curve, we get very good constrained distance, which is around 0.1 astronomical units. The grain size can't be constrained with our observations. And when we consider only the insignificant H-band observations, this is the yellow curve in D. The dust is located at larger distances at around 0.3 astronomical units. And of course, if we consider all of the observations, so all H-band observations and the mid-infrared observations, this is a superposition of a case C and D, which ends up in D, and which is also at medium distance. Then. This brings me to my summary. The results have been accepted recently. This is indeed the very first peer-reviewed publication of MATISSE data. It's more the first L-band detection of hot exozodiacal dust, and we can not find constraints on dust grain size or on the dust material, but we can constrain the distance of hot exozodi between 0.1 and 0.29 astronomical units, which gives us a dust temperature of around 900 to 1400 Kelvin. Then I thank you for your attention.
Many thanks, Florian, for this nice talk and this very nice result. There's a question in the Slack from Olivier, who asks, what new insight does that bring on the dust production scenarios?
Yeah, this is at the moment hard to say for this system, because we have here this near-infrared variability, which makes it difficult because we compare here observations from 2012, 2013, and 19. So at the moment we can, the best way would to have simultaneous observations. Then we could really say the dust is located in this and this year at this and this position. When we would have this information, we could find some new conclusions about the dust production scenario. So what we need to answer this question, or what I would need to answer this question, is more observations simultaneously from L-band and H-band, and then we could go on a step further.
Thank you. There's also a question by Lei Chen, who asks whether you can constrain the grain size.
Why or why not? I can't constrain.
Whether you can constrain the grain size.
No, I can't constrain the dust grain size. That's right. Because we are at slightly, or we are at small grain sizes here below 1 micrometer. If we would have larger grains present, there would be some more fraction of scattered radiation, which we indeed can't see here. So it's very difficult to constrain the dust grain size.
Okay, I had a question myself. So these were observations done with the ATs. I was wondering whether with the UTs you would be able to do observations in the N band to say something about the dust properties, and whether you would have long enough baselines in that case to resolve the problem properly.
I'm not completely sure about it, but I would I think that the resolution is not high enough then, because we have smaller baselines.